So in this lecture, we will learn about L1 regularization and sparsity. So first, what is L1 regularization and why we need to use it? Okay. So first, what we'll get from our L2 regularization? Just write down these equations. Then we'll see how it is useful in L1 regularization. So what we'll get in our L2 regularization? L2 regularization is all about outcome of minimum W summations I is equals to 1 to n, that is our number of data sets in our training sets, log of 1 plus exponential minus yi x transpose w transpose xi plus our hyperparameter into our L2 norm of weight vector. Okay, this is our L2 regularization optimization problem. This will call our loss functions in L2. This will call our logistic loss. Simply, this will call our logistic loss function, and this is our L2 regularizer. Okay, this will see, and this term. And this term, we see that when this term will get that 0 when zi tends to plus infinity, then this two are useful to avoid our overfitting problem. When this zi tends to plus infinity, when it will occur, implies that it will occur only when wi tends to plus infinity or wi tends to minus infinity. Because of why? Because we know that wi, because we know since zi is our signed distance. Signed distance means yi w transpose xi, and xi and yi are both coming from our training data sets. It is totally independent from us. Just we handle our w. So zi tends to plus infinity only when wi tends to plus infinity or wi tends to minus infinity. Okay, in such situations, we see that we have faced a problem. This problem is called a overfitting problem. Okay, this problem is called a overfitting problem. We have faced this problem here. Now, one question is here. So, what is this question? Let's write down this question. What is the question arising? One question we have faced here. This question is what is our alternative? This is a L2 regularizer till now we have seen. Now, what is the alternative of this regularizer? So, if we write it, alternative to L2 regularizer, then what it is? So, in alternative of regulator, here in logistic regulator, the popular one is the L1 regularizer. The popular is the L1 regularizer. Okay, L1 regularizer is the popular one. Here in L2 regularizer, we have seen that. We have seen that in L2 regularization, we have used what? We have used L2 norm. Okay, we have for W, we have used here the L2 norm as regularizer. Okay, and here we have used L1 as regularizer. For L2, here we have used for L1 regularizer. Okay. Now, what is our L1 regularizer? Just we see our mean Cosquez distance. Okay, from mean Cosquez distance, L1 regularizer is nothing, simply simply regularization, sum of its absolute value. Sum of, since we know that W is a d-dimensional vector, sum of its component with absolute value. Absolute value. Okay, this sign is called absolute. Absolute is this. Okay, this is signed absolute value. Mathematically. Okay, this is a L1 regularization. Here we, instead of L2 norm, here we use L1 norm. So now what will be our equations if we apply regularizer term? Our mathematical optimization problem will be arc minor over W. Logistic loss for our training datasets, it is same as L2 and L1 also. It is just same. Now the main, first write down it. Logistic, sorry, logistic loss for training data. Okay, and other part is our L1 regularizer term. Okay, and this lambda we called it as hyperparameter. This term is called it as hyperparameter term, and this is simply a L1 regularizer. We called this term is a L1 regularization because of here we used L1 norm or mean cost distance. So it is useful to avoid. It is useful. When it is useful, it is mainly useful to avoid our infinity. It will avoid what? Wi plus infinity or Wi minus infinity. So it will help us to avoid this. Now come the concept of sparsity. What is first? What is sparsity? Write down the what is sparsity. Then how it apply in L1 norm. This is useful. So first write down the sparsity. What is sparsity? So sparse is nothing. Simply sparse means, suppose write down the example. Our W is what? Our W is a set of vectors which is subcomponents W1, W2, W3, up to W. It is d-dimensional vector W. D is Wi is the component of W. Though this is said to be a sparse vector, this W is said to be sparse. This is said to be sparse if solution to logistic regression is said to be sparse if many Wi of W is 0 or 0. If many Wi, most of them are 0, then this vector is called a sparse vector. Okay, I think you are all clear about it. Then this vector is called a sparse vector. And we know solutions of the logistic regressions means what? Solutions of the logistic regressions is simply W star, means optimal W, and just write down it. It will be W means what? Solution of logistic regressions. Okay, solution of the logistic regression. Now, solution of the logistic regression is called to be a sparse vector if many of the components are zero. Okay, if we use L1 regularization in logistic regressions, then all the unimportant component or less important component means what? Unimportant or less important features becomes zero. Okay, if we use simply, why we use L1 regularization instead of L2 regularization? The main concept is, if we use L2 regularization, then many less important features that we have not used in our data sets, then it will take a small value and it will increase our time complexity. But here advantage is that if any features or any features is less important or unimportant, then just we have taken its component at zero. This is the main concept. Just write down. If we use L1 regularizer term in the logistic regression, then all the less important, then all less important or unimportant features means what? Less important or unimportant features mean what? Means the component of W, that is Wi's. Let's take Wi's becomes zero. Okay. Let's see it graphically. Suppose let's take our F1 features. In dataset, they have D features, F1 features, F2 features, F3 features, F4 features, similarly Fi features, similarly FD features. Okay, this is our features vector. And for this features vector, we have finally we got the W. This means weight vector. For features 1, we got W1. For features 2, we got W2. Feature 3, W3. Features 4, W4. So features WI. Features we got W. Okay. And let's take. This is a less important feature. This is a less important feature. So our L1 norm is said that if we use L1 norm, then this term will become zero. L1 norm is said this term will become zero if we used L1 regularizer. If L1 regularizer used. Okay. But if we used L2 regularization in this case, if we use L2 regularizer, if we use L2 regularizer, then Wi will become a small value, but not necessarily become zero here. Okay, just main difference. If we use L1 regularization, then it will become perfectly zero. But if we use L2 regularization, then this term will carry small value, but not necessarily it will be zero. Regularizer. Then wi become small value. But not necessary it will become a 0. Okay, but not necessarily it will become a 0. Okay. Now the question is now anyone simply asks a question. Why does L1 regularizer creates this sparsity in W as compared to L2 regularizer? Means what? Why this L1 regularization create the sparsity in W as compared to L2 regularizer? That's right. Question is that why does this L1 regularizer create sparsity in W as compared to L2 regularizer? Anyone? So to prove this problem, we have to wait some time, because when we come in optimization chapter, then we learn it. Why L1 regularizer create this sparsity. Okay, just I request you be patient. Just wait some little time. When we come into this chapter, optimization chapter, then we just put this statement. Okay, it will be proved when we come into optimization chapter. Okay. Now, one thing is that elastic net. So don't be confused. It is not a neural network. Simply elastic net. What is elastic net? Let's write down this. It is not a neural network. Simple. It is not a neural network. Means what? It is simple. It is not either L1 or L2. This net is either it is a L1 regularizer or it is a L2 regularizer. Hence, it is the combination of both regularizers. Either L1 or L2. Okay. If we write this elastic net in mathematically formed, it will be written as W star is equals to of arc of W summation I is equals to 1 to n, where n is the number of data sets in our training data point, training data number of data sets in. Okay. Log of, we will see this equation many times, so I think you will easily write down these equations. And what is our first L1 regulation? The L1 regularizations, we call the hyperparameter is as W a lambda 1 and the weight vector W, and for L2 hyperparameter is lambda 2 and weight vector is W. Okay. So in elastic net, here we have used, instead of one parameter, here we have used two parameters. and the two parameter is coming from L1 and L2 regularizer. So two hyperparameter have been used. So this parameter is lambda1 and okay, this is an elastic net. So don't first, again we repeat it, this is not an neural network, it is the combinations of two regularizers, that is L1 regularizer and L2 regularizer. Okay, so this elastic net is reaching this. So just revisit this lecture, what we have learned from this lecture. So first we here use the L1 regularizer to create our sparsity. So why we need such kind of regularizer instead of L2 regularizer? Because this regularizer is used to create sparsity. So this, if this regularizer is used, then the less important data or unimportant data, when the L2 regularizer creates its value is small, but here L1 regularizer, this value, less important features and unimportant features values created is equals to 0 for L1 regularizer. And we see this proof. We see this L1 regularizer create the sparsity in W in when we come into the optimization chapter. Now just patient with me. Okay, I think all are clear till